Hello and welcome to the third part of our lecture on imprinting technology. In the previous part, we introduced molecularly imprinted polymers and how you can use them as alternatives for bioreceptors in biomimetic sensor applications. In this part, we'll go a little bit more into detail onto how to make MIPs and how to incorporate into sensors and what that resulting sensor might do and what type of technology you can expect. Now, if you look at MIPS and you try to classify them based on their synthesis procedure, you mainly have three major routes of making MIPS. One is the most straightforward, one is bulk synthesis through free radical polymerization. You can go for a more controlled manner of polymerization, create homogeneous particles through emulsion or suspension polymerization, for instance, or you can directly grow MIPS onto the surface of a chip through surface grafting. And which type of approach you choose typically depends on the sensing application that you have in mind later on. Now, like I said, the most straightforward procedure is to go for bulk free radical polymerization, where you basically toss the monomers into a solvent which do they dissolve. You just add the target and a pre-arrangement step will take place through self-assembly, meaning it will happen spontaneously. Your monomers will form around your target and will interact with the target usually through non-covalent interaction, usually through hydrogen bonding and van der Waals forces. And the monomers will link together already in what we call a pre-polymerization complex. Now, these will just create linear change of monomers if you couple them together like this. So what you do then is add a cross-linker. And in order for the polymerization to actually start, in order for the monomers to click together and form a polymer, you need to add an initiator. You then have to remove oxygen and water from the mixture by purging it with nitrogen and creating an inert atmosphere, and then you're good to go. You can start the polymerization by adding energy. It can either be in a water bed at 60 or an oil bed at 60 or 65 degrees, and the heat will give energy to the initiator to create a radical. This will be a group that will easily connect to other groups, and this will create a polymer chain that will be linked together by the crosslinker, and you will get in the end a monolith, basically a block of powder that you can crush and then sieve to select on size. And you will have all these small MIP particles with the target still in place. Now, obviously, you want the MIPs to rebind the target, so you need to get the target out. For this, we use an extraction procedure called Soxclad, where you heat a solvent, and the solvent will condense down on the MIP and will flush the MIP in continuous fashion for multiple days. And when that is finished, you dry the MIP, and the MIP is good to go. The MIP can rebind its particle, its target. Now, the benefit of using bulk free radical polymerization is that it is very cheap and very straightforward. You basically have to toss them together, wait, crush them, extract them. It's not really very difficult. The problem is that you get very heterogeneous particles. The particles will differ a lot in size and shape, and you can then pre-select them somehow by sieving them off to the desired particle size, but they will still have a very heterogeneous shape, and they will also have a very heterogeneous affinity for their target, meaning that some parts of the mixture will bind more MIP than other parts of the mixture, which is of course a disadvantage. On top of that, you have to put them in a Soxclad procedure that takes time, that takes about a week to extract the target from them. So that's not really ideal for large scale production. And you have a powder in the end, right? You still have to immobilize that powder somehow onto your chip in order to start a measurement. A much more controlled manner of creating MIPS is in controlled polymerization. For instance, in emulsion polymerization, you take an organic phase, usually a water-based solvent, and you add an inorganic phase, usually an oil, and the oil and water don't mix, so they'll form micelles inside the water. And by adding water repellent monomers and crosslinkers in the target, the uh, polymerization mixture will actually be incorporated into these small microspheres, and the reaction will actually take place within these microspheres, meaning that the target or the particles that are formed can never be bigger than the droplets in the emulsion. Suspension polymerization is a similar technique where you use a water-based system and you make microreactors by using surfactant molecules. In this way, like you see in the picture on the right-hand side, you get a much more homogeneous particle size distribution, and the shape is nice and spherical. Other examples on how to do that are precipitation polymerization, where you make a precipitation out of your solid components into your water phase, or you can use a core shell polymerization where you use silica beads that have a predetermined form and you build the MIP around these silica beads. All four of the methods will result in more spherical particles, more homogeneous particles. Now, the benefit is that it's still pretty low cost and relatively so straightforward, but you get a much more homogeneous particle size distribution. Disadvantage is that extraction will still require Soxclet, and you will typically have to mobilize these beads still on a chip to detect your target. To give you an example, a very relatively recent example by Silverio and co-workers from 2017, what they did was before we talked about the pregnancy test, well, they made a similar test, similar lateral flow assay where they changed the test line and they changed the test line where you usually use antibodies towards your target and you use MIPS instead. So what they then do is take a sample that contains uh, the target, which is a pesticide, Triazophus, and to that sample they add the target coupled to an antibody and a fluorescent molecule. So what happens is if no target is present, then all that conjugated pesticide with the fluorescence label on it will bind to the first line, and you will get a very thick, very high concentration reading in the first test line for the MIP and the control line where you have antibodies immobilized too. So you will have two broad lines when no pesticide is present in your environmental sample. However, when there is pesticide present, the pesticide will also be transported to the test line and will bind to the MIP much more with a much higher affinity than the pesticide with the mouse IgG and FITC coupled to it. The reason for this is that the MIP has a higher affinity for the pesticide without the label on it, and will therefore preferentially bind to the pesticide, the bare pesticide present in the sample. And the more pesticide you have in your sample, the less conjugate, so the less FIT-C is able to bind at the test line. So you will get a weaker signal at the test line. Your control line will stay the same, and the weaker the signal is at the test line, the more pesticide is present in your environmental sample. And they use this actually to determine pesticide contamination in wastewater from the agricultural industry. Now, a very elegant approach to overcome the need to immobilize MIPS onto your sensor surface is by directly grafting them. On the top side, you see a schematic representation of how you can do something like that. And this actually was done in our lab by one of our PhD students called Joseph Loden. And what he did was, we use aluminum chips in our lab to measure to do thermal measurement experiments. And what he did was before polymerization, he actually functionalized the aluminum with a crosslinker. And what he then did was use this functionalized aluminum and put the polymerization mixture on top of this functionalized aluminum. So what happened is the monomers will connect to the crosslinker on top of the aluminum and will form a polymer inside that on the surface of that aluminum in a directed manner, creating a polymer layer that incorporates the target. Now, when you remove the target, in our case, we use the designer drugs molecule that's becoming very popular in the pre-corona rave scene, and we imprinted that and we extracted it and then rebind and then did a rebinding experiment where we dissolved some of that powder in water and we were able to discriminate between that powder and a common adulterant. So you could use a sensor like that for doing a routine drugs test. Now, a very specialized version of doing surface grafting is what we call electropolymerization. So what you do is you take monomers and a target that are electroactive, so that have a certain charge, and what you do is you do a voltage sweep. So you put an electrical current over your electrode and you sweep the voltage over the electrode from negative to positive values and back. And what happens is that for every sweep, a polymer layer will be deposited. So you can build up a polymer layer in a very controlled manner on top of your electrode. And then when you're finished doing that, when you have the desired layer thickness that you want, you stop the polymerization and the polymer will cross-link, and you can get rid of your template fairly easily by reversing the potential or reversing the potential of your voltage sweep, and the positive or negative charged target will be pushed out of the cavities, and you will have a nice firm layer that will contain nano cavities that can bind your target again. Now, the benefit for surface grafting is, like all MIP procedures, it's very low cost. You will get a very homogeneous layer on the surface. You can do the extraction by repulsion. Let's say you make an imprint of a negatively charged particle by just placing a positive potential over your electrode. You will push the target out again, and you don't need to immobilize your MIP because you grow it directly onto the surface. The disadvantage can be that it requires a little bit more instrumentation, especially electropolymerization, and it's more difficult to fine tune the parameters. So it's a little bit more difficult to understand when you should stop cycling in electropolymerization, or what type of molecules you should immobilize on your surface. So the actual reaction parameters and controlling them is more complicated. Now, to give you an example, some friends of ours in the University of Leuven did electropolymerization on a catheter, as you can see in the image on the right hand side, and they stripped the catheter, and what they did on one side, they immobilized through electropolymerization a MIP for histamine, and on the other side they imprinted and they immobilized a non-imprinted layer, which is essentially the same polymer layer but without the target imprint, and they were able to insert that catheter into the duodenum of patients and measure histamine there. Now, why that can be very important is that you can monitor histamine inside patients whenever they get an episode of, for instance, irritable bowel syndrome. And this can help in diagnosing people with irritable bowel syndrome, but can also help to understand the disease in a better manner. Now, a different group in China, as you can see on the left-hand side, developed a patch which you can wear on your arm as sort of a hydrogel, and into that hydrogel they incorporated electrode containing gold nanowires, which they then electropolymerize with a polymer containing an imprint for lactate. They rinse the polymer out to remove the lactate, and then they attach the extracted MIP covered sticker onto the arm of a sporter, and when this person is sporting and sweating, the sweat will be transported to the patch into the electrode, and there you can read out how much lactate a person will produce during sporting, which will massively help in studying uh, lactate formation in exercising sporters, and will probably contribute in the future to a more personalized version of training Olympic athletes, for instance. This was part 3 of our lecture. I would like to invite you to visit lecture part 4, where we will discuss how to imprint not only small targets but bigger entities such as cells and bacteria. Thank you for your attention.